direct search method, okay, which is golden search algorithm, right? So our next method is golden section search algorithm. Okay, let's revise about Fibonacci. We have what? In Fibonacci, we have x1, we have x3, right? And then you identify x2 or x4, okay? And then you choose the new interval, okay? This is your current L. And then you will have the next L, okay, plus 1 or this one. Depend on the value which refer to if you have x2, have x4, and so on. Okay, depends on the cases. Okay, so in golden search, all of you are here. Okay, so in golden search, we still want to find during the line here, okay, but we use x0 here, x0 and x3, okay. So let's say you have a range of LK here, okay, and in finding x1 and x2, right, we use the same ratio. Let's say here we have LK plus 1 and this one also LK plus 1. We use the same ratio. Okay, but for Fibonacci, the difference between x1 and x4 and x2 and x3, we might seem a little bit different because we have to find the value first, right? And then we identify the what we say the value of L here, the iteration, okay, the interval there. All right, so in golden search, okay, in golden search, we have exactly the same value for the ratio. Let's say we want to find the ratio by using LK over LK plus 1 here equals to a constant named tau. So this tau here is called golden ratio. Okay, and then let's say we have another interval. We have another interval, and this is your LK plus 1. Sorry, L2, X2. LK plus 1. We have this interval, okay? And then we want to find X0, X2. This is your new interval. Okay. This one becomes new X3, right? Then we have another X1 and X2. And then we have another interval. Let's say LK plus 2. All right. This one also LK plus 2. Still, we have the same ratio. In golden search, we are going to use the same ratio here, which given by golden search. Okay, so in order to find the next value for each iteration, we are going to use this value of tau. Okay, the golden ratio. So how can we find the value of t here, the tau here? Okay, from the figure, okay, let's say we have LK plus 2 plus LK plus 1 equals to LK. LK plus 2 plus LK plus 1 equals to LK. Where does this value comes from? LK plus 2 here. LK plus 2 plus LK plus 1 will give you LK, right? Because this LK is actually comes from LK plus 1. And then once we choose the new interval, we have this LK plus 2. So LK plus 2 plus LK plus 1 equals to LK. Understand or not? Are you clear, all of you? Okay, so now this LK plus 2, we can deduce this LK plus 2 by LK plus 2. This one is just for simplification process. How can we prove the value of tau here? Okay, as you can see, LK plus 2 is actually LK plus 2 over LK plus 1 times LK plus 1 over LK times LK. Where if we can omit the value here, we can have LK plus 2 again. Okay, but now from the figure, we know that LK plus 2 over LK plus 1 equals to tau. Okay, and LK plus 1, sorry, LK plus 1 over LK, this one terbalik. LK plus 1 over LK equals to tau. Okay, times with LK. So we have tau square LK. All right, clear now? So from here, if we can simplify by dividing with LK, we have equals to 1. All right, so LK plus 2 now is equals to tau square. This one, substitute with this one. Okay, LK plus 2 over LK equals to tau square. LK plus 1 over LK equals to what? LK plus 1 over LK equals to what? Anyone? No one? What is the value of LK plus 1 over LK? Yes, this is the value of tau. Okay, equals to 1. So solving this quadratically, we will have tau equals to set of 5 minus 1 over 2, which is 0.61803. So this is what we call a golden ratio. So we are going to use this golden ratio to find the number of interval in the golden search method, where we have here x0 to x. In order to get this as x2, we just have x0 plus tau L, and in order to get the value of x1 here, we have x3 minus tau L. Okay, let's take a look at the algorithm. Okay, so let's discuss the maximization problem today, because last class we have discussed minimization. The difference is only the choice of the new interval, where we have to take a look at the value for function. Alright, so now we have maximization. The golden search technique for finding the maximum of a unimodal function over an interval a to b can be summarized as below. So determine the initial interval a and b and the desired accuracy. Okay, we have the interval, we have the epsilon, then we set x0 and x3. Okay, our interval is in terms of x0 to x3 here. Okay, and L is the value, is the difference between x3 and x0, x3 minus x0. So find x1 and x2, which are placed symmetrically with the distance tau L from one end of the interval by using the following. So the difference between x0 to x2 and x1 to x3 is by tau L. That's why the next value is given by this. Okay, then evaluate fx1 and fx2 and then determine the new uncertainty interval. So actually, as you can see here, the interval is quite identical with Fibonacci. Okay, by looking at the cases there, then we can define our new interval. So the difference between Fibonacci is the exact value of golden ratio, okay, where we are going to use the same exact value of tau there, okay, and then we don't have to find the number of iteration. Okay, so in Fibonacci we need to find n first. Right, so in Fibonacci we need to find n, and then we need to find L2, and then we have to find every value of x2 and x4 here depends on the L value. But looking at the figure, for each iteration, we just have to choose the value there. Okay, in golden search, we need to use the tau value. Okay, let's take a look at this example. We can do it one by one here. Okay. Okay, any question before we start with this? As you can see, from the algorithm, we need to have A and B and the desired accuracy, epsilon. Okay, so usually epsilon is given. And then for this golden search, we can also check the number of iteration by some calculation. Later I will show you. But no need to find the number of iteration first before you start the calculation, because we are going to stop at L less than epsilon. Okay. So now let's start with this example. Okay, so first step, we need to identify A, interval A, B, and the desired accuracy. So what is your A and B? Here, define A and B, where A and B is given 0, 1. So your A equals to 0, your B equals to 1. All right? And then your epsilon is given by 0.05. So we should stop the calculation once we attain L less than epsilon, or until the desired number of iterations have been completed. Okay, let's focus on the first part first. We stop when L less than epsilon. Okay, now what is the value of L? Okay, in iteration number 1, what is the value of L? For interval 0 to 1, L equals to what? Yes, L equals to 1. L equals to 1. So, by figuring out this, we have from 0 to 1, okay, we need to find what is our x1 and x2 because this is your x0, this is your x3. Okay, remember your x0 equals to A, your x3 equals to B, and L is x3 minus x0. Then we need to find x1 and x2, which are placed symmetrically. So x1, how can we find x1? So x1 equals to x3 minus tau L. x3 equals, x2 equals to x0 plus tau L. So just substitute. Your x3 is 1, your tau is 0.61, your L is 1. So what is your x1? Your x2, x0 is 0 plus with 0.618 times with 1. Then you can have here equals to 0.382. This one is 0.618. And then identify the value of fx1, fx2, which is substitute to the value of function there, where the function is x times 1.5 minus x. Then you got your fx1 equals to 0.427, 0.545. So x1 here equals to 0.382. This one is 0.618. Right? fx2 0.545, fx1 0.427. Now take a look at the cases. Okay, then determine the new interval by considering the cases below. fx1, fx2. Now we take a look the value of x1 and x2. fx1 less than fx2. Okay, when fx1 less than fx2, your new interval is x1 to x3. If your fx1 greater than fx2, then your new interval to x0 and x2. Okay, as you can see, without considering the algorithm there, you can see that fx2 is greater. And this is maximization, right? So your new interval should start from here. Okay, understand or not? Then proceed with the next iteration. What is your new interval? Your new interval is what? x1 and x3, which is 0.382 to 1. Okay, now this is your new x0 and x3, where L equals to 0.618. Then you have to find again what is your x1, what is your x2. Is that clear or not? But this x1 is actually come from this. Okay, if you use the formula, you can get the same value. 1 minus 0.68618 times with 0. So you will get same value, right? Yes, same value. So actually, this x1 come from this So since this is your new x0 and this is your new x3, so this is your x1. And x2, again, x2 equals to x0 plus tau L. Just substitute the value there. x0 is 0.382 plus 0.618 times 0.618. Then you get your new x3. Okay. Anyone want to figure out this value, which gives you here 0.7? All right, clear now? Anyone has question? Okay, looking at the graph, the figure here, what is your new interval? What should be your new interval? Okay, x1 and x3. Right, good, understand. So your new iteration should focus on the value from 0.618 to 1. So this is your new x0 and x3. So you need to find again what is the value in between them. All right, is that clear? You can find your L here. Okay, so you need to proceed the calculation here until you reach L less than epsilon, where epsilon is given by 0.05. Okay, understand or not? So the difference between the maximization and minimization is the choices of your new interval. All right, clear or not? Anyone has question? Again, you have to find your x1 and x2 by using the value of tau. Okay, so by this example, you should proceed with up to iteration number 8. Okay, this is your the last calculation. Okay, please proceed. Iteration 8, where you reach the new interval until and L is given by 0.0218. Okay, as you can see, this is less than epsilon. How to choose the cases? Okay, refer to this. Case A and case B. Refer to the value of function. Okay, you have to take a look at fx1 and fx2. When fx1 less than fx2, for maximization, choose x1 and x3 as your new interval. Okay, new interval means it will become x0 and x3 again, right? Clear not? And if fx1 greater than fx2, your new interval is x0 and x2. All right, clear? Okay, So that is how you do golden search iteration, golden search method. Okay, we stop when L less than epsilon. Okay, so what is the difference between this golden and Fibonacci? It's quite identical. All right, and we don't have to find N. We don't have to find number of iteration first. Okay, in Fibonacci, we need to identify the number of iteration and then we can just proceed with the calculation reaching the number of N. But for this golden search, we just follow the value of epsilon and we stop when L less than epsilon. Okay. So the stopping criteria is epsilon and only one function need to be calculated. Same with Fibonacci, which is here is store and in Fibonacci is L2, right? We don't calculate L2 more than once, only one calculation. In golden search also, one calculation of store value there. So that is the comparison between Fibonacci and golden. All right. And that's it for golden search algorithm. Is there any question? Okay. If we want to check the number of iteration, it is given by, okay, this is for checking purpose. Checking the number of iteration, it is given by store to the power of n times with L1 less than epsilon. Okay, we have tau 0.618 to the power of n times with L1. Our L1 for this example is what? Our L equals to 1 less than 0.05. Okay, and then here we have ln and ln 0.618 less than ln 0.05 and n here can be equal to what? N greater than 6. Okay, so this is for approximation value of number of iteration. Okay, because we don't have the exact value of n in Fibonacci, we have n at least 8 iteration because we have the value of fn. In golden search, we just have n greater than 6. So n can be anything. So for this case, we stop n equals to 8, which is greater than 6. Why we stop at 8? Because L less than epsilon. Okay, any question? Just use L1 only because we have multiple value of L. L1 comes from the value of L in iteration 1. All right? Clear or not? Okay, please proceed with the calculation. If you have question, you can ask. Any question? Okay, so in the last iteration, you just need to conclude with what is your maximum point. Okay, for x1 and x2. Oh no, x only, right? What is the maximum point of x, which give you what is your maximum value when using the x there. Okay. Note is different. Okay, look at your notes. The first one, the first one there is for minimization. Okay, I use the second part, maximization. Am I right? Look at the second part in page 4. for maximization. Okay, be careful. This one is maximization problem. So I use the second part of algorithm in the not given. Okay, Leong? Am I right? All right. So just in minimization, just compare the value of x1 and x2 there. It's quite different with maximization. The choice of new interval is depends on the function of fx1 and fx2, referring to cases in maximization or minimization. Okay, so in this example that we have discussed, this is maximization problem. That's why if you can see in the figure, we choose the higher one. This one. Okay, we choose the highest one. Okay, proceed, please proceed until iteration number 8. Once you got it, then you can stop. Means you understand. Okay.